So thank you for joining me to watch a lecture video on laser physics course. And this time the lecture video will be about Fermi's golden rule. So what this golden rule is about, it basically just tells us how we can really calculate the transition rates. And because we can connect the transition rate into the kind of like lifetime associated with this kind of like excited state, this really gives us a quantitative tools to understand many things happening in many branches of physics. And this is really general, this Fermi's golden rule and how it's being applied in photonics and optics and also other branches of physics is really more general than our description on lasers. And I'm trying to understand lasers, so please be noted that this is actually like a very fundamental rule and piece of mathematics that we will be introducing to you next within our slides. So I will now just get started. Like I already was trying to say in my introduction, this is a very fundamental equation used in really many branches of physics where we can describe processes using Hamiltonian operators and slight perturbation of these Hamiltonian operators to actually like induce some kind of dynamics into the system. So that can, for example, be in our case, the excitation of an atomic two-level system from the ground state into the excited state. It could also be electron scattering processes, so more on the kind of like realm of solid state physics or condensed matter physics. So for example, we could be interested in about like electron scattering, or we could be interested in electron phonon scattering. So those would be the kind of like questions that we might be interested in solving to better understand, for example, electrical or thermal conduction taking place within a material. So this is really going way beyond laser physics, optics, and photonics. Another example that they came to my mind is a electron excitation process within semiconductors. So for example, if you would be looking at electron hole recombination processes, these Fermi's golden rule can be used to calculate things and understand things there. And there are many other applications of this rule within physics. Okay, let's then start the actual business. So let's first note that if we look at the kind of limiting value of the cardinal sign terms in the expansion of CE term, we see that they start approximately looking like a Dirac delta function. So if we take a kind of limiting value of time expanding or going over all the way towards infinity, this cardinal sign term there within our equations like really can be approximated that that's a kind of like a delta function. So essentially this kind of limiting value for this cardinal sign is a 2 pi times t times a delta function of this x parameter there within the equations. And now we plug this, that how that connects this piece of mathematics with our physics. So we have a similar kind of limiting value, but now within the cardinal sign, instead of x, we have this 1 over 2 times omega naught minus omega terms, and that's how our mathematics looks like. So now we can really approximate this, that this is essentially pi times t divided by 2 times a delta function of omega minus omega naught. So basically we get some kind of like non-zero value, or actually like an infinite value when the omega frequency equals the omega naught. So that's the kind of transition frequency within the two-level system. And this above allows us to calculate or state that after a long time has passed, so essentially when t times delta omega is a far larger number than unity, the rate of absorption W is really approximately given by W absorption. That's the time derivative of the modulus square of the CE expansion coefficient. So that's approximately pi over 2 times the Rabi frequency squared times a Dirac delta function of these frequencies. And please recall that the Rabi frequency was defined using the transition dipole matrix element associated with the transition from the ground state into the excited state, or written explicitly, that depends on the Hamiltonian, on the interaction Hamiltonian. So this expression is essentially known as the Fermi's golden rule, in our case applied for a simplistic two-level system. Now let's then finally spend a little bit of time of understanding how we can generalize this result so that you can really appreciate that this can be used in many places in physics. So we can really generalize this for any Hamiltonian of a dipole-like interaction. and for any discrete or continuous distribution of frequencies, delta omega around the central frequency omega naught. So basically, we do not need to be restricted to these kind of like very simplistic scenarios. And for example, when we are looking at a continuous distribution of frequencies, and if you would have a more than single final state of f, then the transition rate W would be calculated by summing over the frequencies. So basically the rate of transition, and that's the kind of inverse of the radiative lifetime, is basically equal to 2 pi divided by the reduced Planck constant squared and integral over frequencies. And here we do have this interaction Hamiltonian calculation that we have already covered. And then we have this delta function over the frequencies of f, omega f minus omega I. So this is basically like what we can do if you want to generalize to kind of distribution of frequencies. So now we kind of like really integrate over different possibility of frequencies. And here is basically the kind of part of the magic that happens, that the kind of depending on the initial state and of the final state, we might either have a more probable transition taking place if the interaction Hamiltonian like overlapping and allowing this kind of transition to take place, or if it's not. So like depending on that, this either can be large or small, a value here. And then we are integrating over all the possibilities of frequencies. And in principle, they could also go over and sum over possible final states. So let's now try to generalize Fermi's golden rule even further a little bit, so that because we can really calculate many kinds of transition rates using this Fermi's golden rule between different atomic states or electron states or semiconducting like conduction or valence electron states. So the rate of transition from an initial state I into the final state essentially can be written that it's a 2 pi divided by the Planck constant reduced 1. And then we have this modulo square of the interaction Hamiltonian. And then we have some density of states that we are moving from the I state into the F. So here DOS I to F is basically the density of states of the respective process. So depending on what kind of system we're looking at, what kind of processes we're looking at, the density of states might vary. So for example, that might be a joint density of states of state pairs, as for example, in kind of semiconductor physics, when we are like wanting to raise an electron from the valence band into the conduction band, or for example, we want to see a kind of like matching of electron with a hole. So that this is basically what I want to say here. Okay, for example, the Fermi's golden rule to calculate a transition probability rate for a photon to raise an electron from a valence band V to the conduction band C. So now we are really, for example, interested in a semiconductor physics, in a direct band gap semiconductors, what happens. So we might be, for example, interested in understanding how a photovoltaic cell behaves, or how can we pump a semiconductor laser, or like what else. Many things could be looked at in terms of semiconductors, and this kind of calculation would give us a means to quantitatively do those kind of calculations. So basically now, this kind of process, application of Fermi's golden rule to kind of try to estimate and really quantitatively calculate how probable it is that this kind of transition takes place. The gamma from a valence band electron going into a conduction band is basically given by 2 pi over reduced Planck constant. And now we are integrating over different values in the Brillouin zone of different wave vector momenta. So basically k values. And this is basically a 3-dimensional volume integral. So that's why I have this vector notation here. So essentially k equals kind of like kx, ky, kz components. So this kind of like linear momentum can point out in every possible direction in 3-dimensional volume. So we are integrating over different kind of directions where the electron wave function can go. And now we have the familiar interaction Hamiltonian there, giving us a probability. And then we have basically kind of like a momentum energy conservation taking place within that integrand that we are having here. So essentially, why I wanted to have this generalization here, I wanted to just point out that if we would go beyond like our simple treatment of atomic media that, for example, behaves like a gas, if you go into a kind of like a crystalline materials and into the realm of solid state physics, then we should really extend the kind of like integration of all these different possibilities over an integral over the Brillouin zone. So then we should really kind of like take into account the kind of periodicity and the subsequent band structure of our solid piece of a material when we are doing these calculations. And then when we are calculating that can we do this kind of like transition from the initial state into the final state, and here I have these sub labels to kind of like noting that this is the kind of initial state in the valence band, and this is the final state in the conduction band. We have some kind of interaction, for example, light shining into the semiconductor, or sunlight if you're looking at the kind of photovoltaic cell behavior. And now we are kind of like integrating all the possibilities that can this frequency of light be absorbed into this semiconductor. And since we do have a band structure within the semiconductor, so we need to take into account all the possibilities that what kind of states we may have. And finally, this delta function here tells us that in addition to this kind of like matching of linear momentum of the states, we also need to be having a matching of energy so that this kind of transition can take place. So we also need to take into account the factor that depending on the different electron wave function state, it also is associated with a different energy. So that's why I have this like EV, the valence band energy, and then I have this K value here, so that the energies now really start depending on the band structure of our material. And the same thing applies for the conduction electron state energies. And then we have the transition, we have the energy of our impinging photon. So this is also kind of like statement of energy conservation, but I wanted to kind of like clarify with this notation that indeed things get awfully complicated when we go to a kind of more realistic three-dimensional crystalline materials because of the band structure theory of solids. If you're interested really about that kind of mathematics, like we have a great course on solid state physics, and we happen to have those videos also openly available on YouTube. So please, feel free to dive into those lectures to get a more information of what happens when we go and study periodic structures. But here I will conclude, and I will thank you for listening me mumbling about Fermi's golden rule, and of course the course is laser physics. Please stay tuned for the upcoming videos. Thanks and bye bye.